Hello everyone, hope you are doing good and welcome back to our channel. Today we are at problem of the day 19 of the Geeks for Geeks December challenge, and we again have an easy question in front of us. It's called Rightmost to Friend Bit. So as you can see, we are given two numbers and we both are integers, and we again have written integer as the output. Okay, let's see the question first. So given two numbers M and N, the task is to find the position of the rightmost different bit in the binary representation of numbers. Okay, there are so many new tabs. I am expecting that the audience which is viewing this video is from mostly a fresher audience, or those are in the final or the third year of college. Okay, so they are saying is that the task is to find the position of the rightmost different bit. Okay, what is bit? We'll come to that, but just now, just understand that we have to find the rightmost different bit. So among all the different bits, you have to find the rightmost one among the binary representation of the numbers. Okay, if both m and n are same, return -1. Remember one thing: if two numbers are same, obviously their binary representation is also going to be same. In that case, there will never be a different bit. Okay, that's why they are asking us to return -1 in that case. So let us see some examples now. They've given 11 9 as example, and I've also taken the same here. Okay, let us see that now. So if you do the binary representation of 11, okay, see there are, I guess you would have learned these things in the first year of your college. And if you have taken C++ in the CBSE, then might be, in 12th standard, you would have seen that how to find the binary representations of a number. So this is the decimal part, and this is the, a binary part of it. Okay. So if you talk about 11, this is the binary representation of 11. If you talk about 9, this is the binary representation of 9. If you want to know how to interpret it, it basically means that this is the 2 power 0 place. Okay, this is the 2 power 0 place, this is the 2 power 1 place, and this is the 2 power, yeah, this is 2 power 3 place. Okay, so this refers to 8, this refers to, 2, this refers to 0, which is, sorry, 2 power 0, which is 1. So it basically means that 8 plus 2 plus 1, okay, which is 11. Similarly, this refers to 8 and this refers to 1, so 8 plus 1 is 11, sorry, 8 plus 1 is 9. So these are the various decimals and their binary representations. What they're asking to do is to find the rightmost different bit. Okay, rightmost different bit. So if you see in this case, you can see 1 and 1 are same in this case. Okay, see, right, we have to start from, see, the question asks for rightmost, right? So we'll start from the right itself. Okay, so we'll go from right to left. So this is same again. Okay, so this bit you can see is the different one. Okay, so this is the rightmost different bit. So what is the index of it? It is 2. Okay, so we have to return 2 as the answer. Okay? That is what is expected out of us. uh, few days back, I think 1 or 2 days back, we had learned what is XOR operation. Okay, in the same Geeks for Geeks challenges, we had learned what is XOR operation. So by the way, what is XOR? If I take XOR of 11 and 9, what I'm going to get? See, XOR basically means, see, I'm talking about bitwise XOR. Okay, do not confuse it with the other one. This is the bitwise XOR. XOR means that if two digits are same, the answer will be 0. If two digits are different, the answer will be 1. As simple as that. Okay, so if we take the bitwise XOR of these things, what we'll get? See, these two are same, right? These two are same, so the answer will be 0, right? These two are different. Okay, so what is the answer? It will be 1. Okay, whenever the different bits are different, the XOR of them will result to 1. This and this are again same, the answer will be 0. This and this are again same, what is the XOR of these two? The answer will be again 0. So basically, if I take XOR of any two numbers in a bitwise way, I am going to get a number such that the binary representation of that number will have 1 only in those places such where the binary representation of the previous numbers are differences. Okay, for example, this and this are different, right? So I will have 1 here. So one thing is clear now. See, they're asking right more different bit, right? So right most different. See, this different part is now sorted. Okay, I have now found a way in which I can check which are the bits which are different. Okay, now they are saying to find the rightmost one. How do I find the rightmost one? Okay, again I will start from left. Okay, again I will start from left, and I will have to see which of them is one. There are many ways to do it. See, there are ultimately many ways. In Python, you also have the opportunity to convert, for example, this number, you save it, you can also convert to its binary representation in a string form, and then you can search the position of one in that, the utmost position of one in that. That is also a way. You can try that also. But in this case, I will let me show you something which is really practical, and you will get something more to learn out of it. Okay, so we'll use the right shift here to understand how it works. Let us see. See, what I will do is, if you have to find the, see, remember one thing: if two numbers are not same, definitely they will have some difference. Okay, definitely at least one will be there which is different in them. Please make this one very very clear. Okay, if two numbers are not same, definitely there will be at least a bit which will be different in both of them. Okay, one thing is clear. Next thing is how to find that. I have to find the utmost one. Okay, so first I will check this 0. If it is 1, then we are sorted. Okay, our answer is done. No need to check further. We will return this bit. but in this case there is 0, so I will check this. If this is 1, I will return this as the answer. So how to get to know that? Okay. See, when I do a AND operation, what is AND operation, by the way? AND operation basically means that, suppose I do a AND of this with 1, okay, answer will be 0. If I do a AND of this with 1, the answer will be 1. That means whenever the this particular thing is 1, only then the AND with 1 will result to a 1. Okay, as simple as that. So what I will do is, I will use the right shift operator here. Okay, I will right shift this by 1. Okay, first I will check with 0. Okay, I will do, see, whatever is the result of the XOR, that I will do as I've done here. That I will check with 1 first. Okay, this is one of the edge cases. Whatever is the result of XOR, that I will do a AND with 1. Okay, AND with 1 basically means what? It will remove, just if you do a AND with 1, it basically means take only the rightmost, that is a least significant bit, and do a AND with 1. If the least significant bit is 1, then the AND with 1 will result to a 1. Okay, if the least significant bit of this thing, that's the result, is 1, only then you will get this answer as XOR. Okay, whenever I see this is 1, basically means that the rightmost bit is different for both 11 and 9. As simple as that, because this is the XOR result, right? So this is what we are going to. In this case, this is not 1. Okay, so what we'll do is, we'll right shift this by 1. Okay, if you right shift this by 1, what happens? Right shift basically means all places will shift to their right for one time. Okay, so this one, now see, these things 001 will come as it is 001, and a new 0 will be added now to the left. Okay, this will be newly added. So now I will again do the same thing. Again, I will do AND with 1. In this case, if I get a 1, that means I have got the answer, and I plus 1 will be the result of it. Okay, just let me show you in the code way. Again, then you will understand better what we are doing. Okay, so if m and n are equal, simply return -1, because if two numbers are equal, definitely there will never be a bit which is different in them. Okay, that's, I am doing XOR result of m and n. Okay, I'm doing XOR operation, bitwise XOR of m and n. Okay, if next I am doing XOR, that is whatever the result of that XOR, I am doing an AND with 1 to check if the LSB of that result is 1. If the LSB is 1, that means for the first two number, that is m and n, the LSB was different. If that is the case, simply return 1. Okay, if that was not the case, we'll proceed further here. Okay, we'll proceed further here. Okay, what I'm doing, I'm running I between the range 1 to 32. Why 32 here? Again, okay, this you should actually try to comment it out. Please take a minute to think why I'm doing 32. Please comment it out. I will explain you in the end of the video. Okay, I expect you to comment it out. Okay, please check it yourself. You can Google also, right? So okay, let me tell you this. Why we are doing 32 is because, see, normally whenever integer is stored in most of the programming languages, it is stored in a 4 byte space. Okay, 4 byte. 4 byte in the sense like 4 into 8 bits. Okay, which is 32 bits. So at most we can do is 32, right? That's why I'm doing till 32 only. Okay, so yeah, this is the case. First I will see, remember, I'm doing XOR by 1. Okay, so XOR result, I right shifting it by 1 initially, then maybe 2, then maybe 3, and then so on. Then I'm doing AND with 1. Okay, AND with 1, and then I'm checking 1. That means this is basically done to check which bit of it is 1. Okay, which bit is of the XOR result is 1. Based on that, my answer will be there. Okay, that means, suppose in this case the second bit was 1. Okay, so if I do a left shift one time, okay, I am doing a left shift one time, that is I is 1. In this case, I am getting the answer as 1. Okay, I'm getting the answer as 1, as you can see here. Yeah, if you do a right shift by 1, you are getting this as 1, right? The LSB is 1. No, the least significant bit is 1. In that case, this operation will be true. Okay, this operation will be true. Then I have to return the answer. What should be the answer? Remember, in this case, this was the second bit. After making it a right shift by 1, it becomes the rightmost bit. That is the least significant bit. So answer should be I plus 1. Okay, answer should be 1. I plus 1. Why like that? See here. In this case, they have also written 2, right? They have not written 1 here. Why like that? Because it was the second place, right? This is second place from the right, right? That's what we are doing here. We are returning plus 1 here because, see, whenever do a left shift, the second position comes to the first position. So initially it was in the second position. So we have to do a plus 1 for the I, and when we have to return it. And see, this return statement basically, ideally, it should never be executed. I've just written it here to, for the program to look complete. But ultimately, logically speaking, this return statement should never be executed. Why? Because, see, if two numbers are equal, they will never have a different bit. Okay, that is sorted. We will come to this part only if they are different numbers, right? If the numbers are different, definitely there will be one bit which is different, and that's what we are checking here. Okay, and we return that part. So there will never be a case where we come to this return statement. This is what my assumption is. Okay, I'll just quickly run this and show you. So I hope you have understood this part, right? We are checking if, see, one by one we are checking. Okay, each with, first we will do a right shift by 1. Okay, then ratchet by 1 will basically mean that the second most position which is there now will become the now will come to the first position. If I do a ratchet by 2, what will happen? The third position will now come to the first position. If I do a ratchet by 4, what will happen? The fourth position will now come to the first position. This fourth position will now come to the first position after the ratchet by 4. Okay, then I'm doing an and with 1 to check if this the result is 1 or not. As simple as that. If it is 1, then we are done. We are getting the result. Why I'm checking for 1? This logic lies in the XOR operation. See, XOR of two bits results into 1 only if they are different. Okay, the XOR of two bits are 1 only if they are different. That's what is the question, right? That's what I initially mentioned. Also, we are talking about different bits. Okay, we are talking about different bits. Okay, and the rightmost different bit. So to ensure they are different, I am doing XOR. To ensure they are rightmost, I am starting from right and doing XOR and by ratcheting it by 1. Okay, as soon as that, I hope you have answered this question. This was the optimized approach. In this question, I did not mention any brute force approach. Maybe like you can suggest me what could be the brute force approach for this. But the first thing that came to my mind is this, and I executed that. Right. So yeah, friend, that was all for today. And if you want to see some more good questions, maybe like you can solve the lead code problem of the day as well. This was the smooth image question. Okay, and this here also we are dealing with bit manipulation here. Here also we are doing a lot of shifting operations and all those things. This is also a bit manipulation here. Maybe you can check this out as well. Both these questions are dealing with the same topic basically. This we are using XOR. That is bit manipulation. This is also actually a part of bit manipulation actually. And in lead codes question also for the today. That's the day 19. We are doing the same thing. Okay. Maybe I can give you the link of this as well. You can check it out. It's really nice. Even the brute force approach will work, but the options approach in this case is we will learn a lot. Okay, about bit manipulation. So yeah, friend, that was all for today. Hope to see you tomorrow. Yeah, thanks a lot.